Are You Feeling Lucky? This is actually the third time I've given this talk. I already gave it at Java 1 and at Seeker in St. Petersburg, Russia, so hopefully you all enjoy it. We'll get right into it. First off, who am I? My name is Matt Schuetze. I'm the product manager here at Azul. As Steven said, I do wrestle both Zing and Zulu product requirements, both from customers and prospects and from the general Java marketplace. I'm also involved in pushing all the Azul product launches whenever anything goes live. And I am an alternate on the Java Community Process Exec Committee. In my spare time, I help run the Java user group here in Detroit, and I like to claim myself a friend of Duke, and hopefully you'll see why in a few slides. And I'm also first to admit that I stand on the shoulders of giants, both in the case of the overall Java ecosphere and in some other ways, and we'll see that as we get going as well. So I'd like to start off this talk by mentioning the view of IoT, and that's Internet of Things. Many people consider IoT to be a cloud-based application in the back, where you might have analytics and data storage of sensor data, and where the front is typically some sort of real physical phenomenon that you're measuring with sensors or taking action on with actuators with some sort of appliance or gateway near the edge. And this model is very simple on purpose, because the real model that we deal with here at Azul looks something more like this. There are various classes of sensors and gateways and communication management, all that pertain, if you're using applications written in Java, to our Zulu or Zing product lines to be used on those both gateway and sort of edge class compute appliances, leading all the way to the back end where you have device controls, data analysis, routing, and sort of traditional enterprise data and logic tiers to manage and sort of control your IoT solution. So this is sort of the picture that we take out to market for where we believe Java has a role in different IoT footprints, and then which one of the products, Zing or Zulu, might make the most sense to underpin that. And we'll use this picture again as we go on to say, what parts of IoT run where and how does it have anything to do with casino games. So that takes us into the real guts of this talk. First off, are you feeling lucky? This is all about casino games, and they're used both as an example for writing applications in Java, but I also want to get into the notion of luck and also chance, and what does that have to do, anything to do with something being fair, or fairness in a game, or in other aspects. And it turns out that under the bottom of any sort of gambling software or any games of chance, you have to use random numbers. You generate random numbers to come up with outcomes, and if they are truly random, then they are not predictable, and therefore they are fair. And where does this all stem from? Well, it turns out that there's a branch of physics called thermodynamics, and it has the study of something called entropy. And in our case, we'll see where entropy comes in as a way to quantify randomness. Finally, I point out that there's one element of writing software that leaves a lot to be desired for the case of randomness and random numbers. And so there is a special place for hardware in generating random numbers. Finally, we'll bring this back into real-world impact on IoT, and there we get into a little bit of return a little bit to the casino games example or case study, but also what can you do to outfit your devices to make better random numbers. So we'll dive in. I'll close this webcam, try to improve on bandwidth, and we'll do the talk. So casino games. What are casino games and why are they interesting here? Casino games are casino games are examples of fun software projects. Why? Well, there's they offer a very strict set of gaming rules that can be captured as software routines, and it turns out you can actually build whole online casinos using software, and Java is actually used by them today. It is a worldwide business. Casinos, the numbers I have show that they're projected to rake in $350 billion worldwide in 2018, which is a big chunk of change, and that online casinos alone are responsible for $51 billion of that. So just playing poker on the web and other casino games is a huge market. And like I said, online casinos have grown in popularity, so they're starting to, they still are a smaller fraction of overall gameplay, but still represent a gigantic worldwide market. I want to get into the notion of when you're playing casino games, especially the online versions of any games, it's now a situation where you're a player playing the game, but you're really playing against the coder or how well the application was implemented. Finally, I want to look a little bit at can the house cheat and sort of skew the outcomes in the house's favor. Can they, or do they, which are two different questions. And then we'll get into some of the games themselves. So when I talk about casino games, I usually kind of think about the more popular ones, definitely the ones I like better. Blackjack is a good one, good card game. Craps, great dice game, a lot of fun in a casino. Roulette, kind of old school, traditional, not my favorite, but a lot of people like it. And then you get into slot machines and poker, and there are, Baccarat and I suppose other games as well. But focusing on these, they have good set rules that you can implement in code and build online versions of just about every one of these. Which brings me to our first webinar poll. Stephen's going to help run this, but I'd like to ask the group, what, if any, of these 5 popular casino games would be your favorite? Blackjack, craps, roulette, or 2 types of poker. Either live or card room or tournament poker where you're playing head-to-head against people, or either online or video. Online is still against other players, and video is only against the machine, but either one of those, so definitely a digital format of poker. So, Stefan, if you can run the poll.
Yeah, it's running right now, so it's collecting.
Excellent, thanks. Yep, I'm starting to see the answers come back. So of these, I would have to say that craps is my favorite casino game. Personally, I like it because everyone at the table is really betting together against the house. Even the stickmen are in your favor, because if you win, you usually tip them. But other games are fun too. Looks like we've got half.
Right, let me close the poll now, okay?
Sure. Sure. So, looks like from our absolutely scientifically proven, statistically significant poll, we found that a quarter of the respondents like blackjack, a quarter like roulette, and half prefer online or video poker. Surprisingly enough, that is the same rough ratio that we had this morning when we gave this talk to our European audience. So that's a pretty interesting trend. No one else likes craps. Oh well, because it's just me. So with that, let's continue to talk about these different games. So when it comes down to each of these game formats, we talk about probabilities of outcomes. And some of these numbers should be pretty obvious. What is a chance of 1 in 52? Well, that's the odds of pulling a particular card from a full deck. What is 1 in 38? That turns out to be the probabilities on a roulette table. There's the numbers 1 through 36, but then there's also the green spaces, the 0 and the 00. So it turns out to be 1 in 38. 1 in 6 is rolling a single die, but 1 in 6 times 1 in 6, or 1 in 36, is the chances of any particular value on a pair of dice. So that's what you'd see on the craps table. And no matter what the raw odds are, or the raw probabilities, every one of the games in the casino has got built in a house advantage, a little small percentage, so that over time, no matter what the actual outcomes are on any set of rolls, over time the house will win. Otherwise, casinos could not stay afloat. So the 1 in 38 is the prime example for roulette. You can pick red or black, which you'd think, oh, it's either 50-50 odds, but the red and the black overlooks the fact that there are those 2 green spaces. So whereas you think you're betting 1 out of 36 chances, you're really not. It's less than that because of the 2 green to offset it. And that little advantage, a few percentage over long terms, is enough that the casino can operate and make a profit. So what do these random chances or odds of occurrence have to do with random selection? Where does the point of randomness in the game? For any card game, the randomness comes in during the shuffle. It's not really during the play out or even the betting rounds, but it's during the shuffle. In dice, obviously for craps, it's the roll. You throw it down the table, bounce off the walls. It takes a path that, while potentially calculable from regular classical mechanics, it's really a chaotic phenomenon, and no one can predict the roll if it is fair, if it's a fair dice and not weighted or otherwise jiggered to come out with a particular outcome. Finally, in the roulette, it's a combination of the spinning wheel going one way and the ball going the other, so that when the marble comes to rest, there's no predictable way to find out where it was. All of these phenomena are sources of randomization, random behavior that's not predictable. And the term we use for that is called entropy. And we'll get into the details of entropy in a moment. But if an outcome of any of these games is predictable, then the game is not fair. If someone, some adversary or some person can predict what's going to happen, they will change their betting for or against you to win. And so the point of all of these games of chance is that predictable outcomes are not fair, and that is the standard by which they're judged. When I went to go look for a little more detail about random numbers, I did find some confirmation that indeed random numbers are definitely used in gambling, any sort of lottery application, but even and there are such devices to generate random values, and we just gave some good examples: dice, playing cards, roulette wheels, and fairly produced random numbers are vital to gambling and even regulated by gaming commissions. So that gave me some promise that, hey, I was onto something when I was looking at random numbers. In terms of, in context of Java, now we're getting into the specifics of why Java is interesting and in the scheme of things. Well, let's look at what a shuffle or a dice roll looks like. So Java's got an API for creating sets of random numbers. It's a fairly simple constructor function, and once you have a set of random numbers, you can pluck each subsequent value off. And here's an example where we wound up with 52 elements of random numbers that form the dex in a card, and then you wind up with your card array as an output. So it's a random set of values. Same happens in this example, but now you're actually taking advantage of the collections framework, where there already is a method called shuffle. So the random number generation and the shuffling is hidden from you, but it's underneath the hood. It's the same thing. Create a set of random numbers and then assign the cards to each one in that array. For dice rolling, same function. Create a random number array. Pull the 6 in order so that you wind up with, or pull one from a value scaled to 6, so it represents the side of the dice. You can see here a nice little histogram that shows the possible outcomes for pairs of dice and their probability. So the least opportune pair is a 2 or a 12, which comes in at 1 out of 36. and the most common is a 7. So different combinations to make up a 7 happen 6 out of 36, or 1 out of 6 chances. But the implementation is the same. Create a set of random numbers and then scale it to the number that you need, in this case 0 to 5 or 1 to 6, for represent both sides of the dice. When we actually try to quantify randomness, like say how random is a process or how random are these numbers that we're dealing with, let's take a look at how are they random and why software alone may not be random enough to keep things fair. So first off, random behavior is noise. It's noisy. It's a highly disordered state, ultimately. And analog circuits, if you actually get into the details of analog amplifiers or traditional electronics, they all have noise. And that noise turns out to be thermal noise from electrons bouncing around in the wires. So it's something that's unavoidable, and it's something you must take into account anytime you design an analog circuit. Digital circuits, on the other hand, since they flip between values of 0 and 1, which might be 0 volts to 5 volts or 0 to 3.3 volts, somewhere in there, they do a fantastic job of rejecting noise. That's their design, is to minimize any sort of noise effects. So the problem is software running on a computer is running in a digital circuit. So there's not necessarily always a great way to get true noise available in software. So we try to come up with a measure of how much noise is there and what is that quantification of disorder that's available. We call that entropy. And it just so happens that we use the number of bits as the unit. So we'll start using entropy as that metric. So where does this come from? Why? I mean, entropy is kind of a weird word. Where is it used, and why are we using it to discuss randomness? It turns out this is one of the places where we do stand on the shoulders of giants. So our first giant is a pretty famous guy. His name was Albert Einstein. And not many people know, because he's more renowned for his Nobel Prizes in general relativity and special relativity, and later on in quantum mechanics. But Einstein was the first to sit down and derive that Brownian movement, so pollen grains moving in a container of liquid, rattling around, bouncing off container walls, bouncing off each other. He proved that that is the behavior of thermal agitation and thermal noise, and ultimately is now considered to be the definition of temperature, the random amount of energy that promotes vibrations of, in this case, translations of particles. And so for that, he won his first Nobel Prize. Then there's 3 other giants on whose shoulders we'll stand next. The first is a French engineer named Sadi Carnot. He's involved in the early work in thermodynamics. He was trying to convert heat into work, energy, and no matter how hard he tried, he always found he was losing heat to the environment and could never get 100% conversion of heat to work. So he gave a name for that lost energy. The losses he called entropy. So every situation that he measured or he found, he determined that there was always going to be loss of entropy to the environment. And so that steered his work, which was then later derived by our next giant, physicist named Ludwig Boltzmann. He actually derived the equation of entropy from statistical mechanics, where now instead of treating the averages of macroscopic systems, he actually studied individual particles and came up with loss of energy, or the loss of or the creation of entropy, as an average over microstates of particles. So the randomness behavior of individual particles. Finally, fast forward a couple hundred years almost, and we get to Claude Shannon, who was a scientist working at AT&T, who was measuring signals down fiber optics, and he came up with a full mathematical treatment of information theory, and ultimately came out with loss of information was uncertainty, but it was powerful, and you could actually devise certain types of cryptography around how much information was carried in a signal. So going back to the Carnot and later the Boltzmann era, they were really talking about the second law of thermodynamics. Second law of thermodynamics says that entropy in an isolated system is always increasing. That means if you actually want to add order to a system, you must add energy to it. Otherwise, over time, entropy will increase and energy will be lost. If you look at the entire universe, which is in itself an isolated system, the way that people restate this statement is that the universe tends towards randomness. I like this one a lot because if I'm at home and my kids and I have done a bad job straightening up the kitchen, my wife will come in and say, look at this mess, why is it like this? And my answer is always, well, the universe tends towards randomness, and so does our kitchen. So very useful. Hopefully you can use that phrase yourself. Secondly, digital circuits, as we said, because they're designed to reject noise, don't have enough randomness. So what does it take to get a source of entropy? Where do we get a way to widen the chances of our random behavior? And that's where we're going to spend the next few minutes. Now, it's interesting that we said that high-quality random numbers are needed for science and gambling and lottery applications, but it turns out, due to the work of Shannon and others in information theory, that you use random numbers in cryptography. So random number generation has this very strong role in creating ciphers for encrypted communication. So every part of the Java cryptography architecture, all of the different models for encrypting traffic, actually use random number generators. So there is a direct corollary to number of bits of entropy available with respect to how you can do cryptographic communications. So that's the real reason this is interesting. It's not just for games. And in terms of cryptography, what does it really mean to be random? Well, it means that encrypted messages look and feel just like random garbled strings of characters that have no obvious pattern. So you've done really well if your encryption is indistinguishable from random characters. Then it will be very difficult for an adversary to figure out the pattern that there is there to decipher what's in your message. Digging into where do we actually get entropy if we don't have enough. This is interesting. It turns out the Java, we already showed you the very simple lines of code to create random numbers and use them, but where does the JVM actually get it? Turns out in every JVM in the JRE lib folder there's a security area, and there's a file called java.security. The default value for the secure random source for every JRE is, at least on Unix-based operating systems, dev random. So what is dev random? Dev random is an API, or it's an interface provided by Linux, where if you just read the file, you get random numbers. So turns out there's two random sources built into Linux, dev random and dev urandom. But the interesting thing about this is that it means that the JVM can be changed to use other sources of random number generators. You don't need to use the one provided directly by the operating system. So so we did a little more research and tried to come up with, well, what are some actual ways you can extend to create entropy pools that give you more than better sources of entropy, inexhaustible sources of entropy that you couldn't get just from the OS alone. I found two actual software routines that can generate something like entropy, but they're still not good because they're still software. They still suffer from the fact that there's not enough noise injection. And I did find that there is software as a service called NetRandom, so you could actually call out to somebody else who's providing an entropy source that you rely on, and that's interesting. But I took it a step further and thought, well, what if you could actually include a physical object as your source of entropy? And I came up with a couple. The first one I like is the lava lamp. Why is that interesting? Well, there's thermal energy in a lava lamp. The blobs of lava are following nonlinear chaotic paths. The lava lamps certainly are groovy, so they're fun to have in your software environment. Sure, why not? But it does have some cons. Lava lamps can spill, and they're pretty hot, so they're a little dangerous to leave around your IoT system. And they're a little bulky for that if you're talking about putting them on a gateway or somewhere near where you want to share gameplay. But it's real. After giving this talk at Java 1, I found there is a company called Cloudflare, and they actually use lava lamps as a source of entropy. They have a webcam trained at this wall with a matrix of lava lamps, and they turn the pixels that they get from all this random motion and behavior into random numbers that they use to then drive the secure communications from their server farm. So a little vindicated, someone's actually doing this. To bring it back down to scales closer to IoT devices, I came up with two others. One is a banana. And why would a banana be a good random number generator? Well, it's got a natural phenomenon of radioactivity. Bananas are concentrated in potassiums, which mean they have real amounts of, measurable amounts of potassium-40. Potassium-40 is a 1.2 billion year half-life beta emitter, so it's emitting electrons, which can be detected. The cons are the detection is a Geiger counter, which is a pretty large device to carry around to measure times of radioactive decays. And of course, banana peels are slippery, so potentially very dangerous. We don't want anyone to slip and fall either in the casino or anywhere else. The other natural occurring device that I like is the Brazil nut, and this is another case of natural radioactivity. The source inside a Brazil nut is radium-226. That itself is a 1.6 thousand year half-life, so not as long as the potassium, but still pretty long. These emit alpha particles, so they can be blocked by a sheet of paper or even the skin of the Brazil nut itself. But it has some other cons. These also would need a Geiger counter to detect the timings of the radiation of the decays and the radiations from them. And when radium decays, it transmutes into radon, so you'd wind up with radon gas emitting from your IoT device. So that's not really good either. But turns out there are real items in the marketplace that can give you good, true random number generation, and they are electronics-based, taking advantage of either thermal, so agitation of electrons causing noise, or quantum, which can be other phenomenon that both of these are small and contained enough that they can be put into, housed into electronics that you can add into your device. So some of these actually I found you could buy them as a USB stick. So not only are they packaged and ready, but you just put them in and you have drivers that can actually access those random numbers. So very easy to integrate into your Java application. So how does it work? How do I get at these secure numbers? Well, I have to go back to the Java source. The random number generators by themselves are not triggering the cryptography part of the JCA. You actually have to use the secure random equivalence. So it's a fairly simple change. Just change the class you're instantiating for both the direct array and the collections APIs. And same goes for dice. Just use secure random instead, and that'll trigger the random seeds needed to create cryptographically secure random numbers to then make your dice rolls and your cards even more random than otherwise. So I mentioned that a lot of these figures of entropy are actually cast into bits. That's got an interesting reason, and it turns out that these probabilities that we're talking about for gameplay are actually pretty small. For instance, 1 in 6 for a roll of the dice, that's only 2.5 bits of entropy. For 1 in 38 on a roulette wheel, it's 5 1/4 bits, and for one card out of a deck of 52, it's 5.7. When you are actually doing cryptography, you would like to have your source of entropy be double the number of bits that you have in your cipher. So if you were going to create a 128-bit key, you'd want to have double that, or 256 bits of entropy. So what would a single roll of the dice be enough entropy for that? No, you would actually need, I guess that would be 10 times that, so, or 100 times that, to get 200 bits of entropy for a 128-bit cipher. So 1 in 6 is not enough, not random enough for cryptography, but it's the higher the number of bits you have, the more secure your cipher is, and the closer your encrypted traffic gets to fair or unbreakable in terms of indistinguishable from random characters. So with that, we'll start to wind up. Why did I care about this topic? Why did it interest me? I care about this for Java for a specific reason. Number one, in the world of IoT, it turns out there's lots of fragmentation in terms of languages and tools and how you actually write applications on both devices and gateways. And for that, Java reintroduces the concept of WARA, or write once, run anywhere. And for that, we're standing on the giants of yet another shoulder. This is James Gosling, inventor of Java, who is a strong proponent of WARA. It turns out we're working with a lot of customers that are using our Zulu embedded product especially to put JVMs onto embedded devices and write their application once and run it on many different types of processors or environments. So that's WARA portability is still very important to IoT. And for security and encryption in specific, I'm the person in Azul that gets asked about it all the time. Any sort of commercial procurement where people are looking at either Zulu or Zing, and they want to know about the security providers in the JVMs and what levels and what types of providers, I'm usually the go-to person that has to answer those. And also, since all of our products provide the Java cryptography architecture, we need to understand what are in those implementations, and they change. They're different from Java 6 to Java 7 to Java 8 to Java 9. So they do evolve over time. You need to be somewhat aware of what's shipping in each product. And finally, we did get asked at Azul to create a Java cryptography extension that can go higher than 128-bit security. So I led the team that produced our Java Cryptography Extension Kit, or CEK, which basically lets you extend key sizes to as big as you want. So much higher than 128-bit. Basically as big as you want to get without using all the computing power available to you. So picking numbers like 256 or 4098 is definitely within the realm of possible. And then finally, so I mean, this is part of my job, so I have to know this well enough to coach people through what does it mean and what's the impact. Secondarily, or next, I did actually experience building an IoT-related game, so to speak. At Embedded World last year, I created the Wheel of Java, version 1.0, and brought that to our booth and let people play to spin the wheel, and I got criticized pretty heavily that the wheel was not fair. Why was it not fair? Well, you could actually predict the outcomes. There were 2 or 3 spots on the wheel that you could land on 80% of the time, so people said that's not a fair game. And yes, it was predictable because it was terribly imbalanced. So what happened this year, or later this year, I created Wheel of Java 2.0. This one was not predictable. In fact, it was very true, and it was definitely a lot more fair in terms of gameplay. And here is another one of our giants, or I said it before, I was a friend of Duke. Duke even visited and spun the wheel, and we wound up in the highlights for the show video made by Oracle, so that was kind of fun. And again, only 3.58 bits of entropy per spin, so probably not something you want to use for cryptography, but yet another source of entropy. Getting back into the realm of casinos, can we answer the question about fairness? And the answer I can offer is yes, it is fair. Casinos are not rigged or fixed. Even the online versions, especially, well, I mean, the table-based games obviously are using physical sources of entropy. Any cheating would be probably found out by either the casino themselves or by gaming commissions that regulate them. But if a casino wants to stay reputable, they will use good random number generator technology, and they're often audited by their gaming commissions to do so. Any casino that's found to be cheating because they have changed the software or otherwise found a way to make games predictable, either intentionally or by accident, will typically be found out and shut down or changed until they are in compliance with fairness. So I feel confident that casinos are fair because people are watching closely. Finally, would Azul care about casinos at all? We build software. Well, it turns out, as I said, casinos are a huge part of the entertainment business. Online casinos alone are projected to rake in $51 billion next year. Floor casinos, even more so. There, the number jumps to about $350 billion projected in 2018. A lot of the different floor games do have electronic components. Obviously, the video games and slots and those sorts are basically compute games to begin with, so are good candidates to actually use Zulu. But even non-video or non-electronic games, you typically have the money counting or other aspects that are electrified and want to be have that data sent back towards the back office. So we feel that there's plenty of use cases on the show floor for Zulu. And then any online action, there we get into sort of a real-time situation. Yes, there's the random number generation aspect, so you'd want to use Java for that, but also for multiplayer online games, you want to remove any sort of latencies. So regular Java can introduce latencies, and our Zing product removes them, so it seems to be a very logical, good fit for online casino games. Finally, Java as a game platform is real. It is out there. There's actually a website called Best Online Casinos that lists available game platforms today that are already, that actually list the benefits of using Java for gaming. And then another site lists the actual gaming companies using Java for games. So a couple of big names in that set worldwide. So it's real. People are using Java for casino gaming, and I want part of their business. That's what it really comes down to. So in conclusion, we feel that IoT is a great place for Java. We think that cryptography and the Java cryptography architecture are core to all sorts of communications and security scenarios that make Java a great platform. And then just general gameplay. All of those rely in some way on good sources of entropy to achieve unpredictability and fairness in outcomes. So the cryptography architecture can be set up to use the entropy sources, not just from the OS, but from extended components as well, giving true random numbers. And the secure random class and implementation is what self-seeds itself to give you the distribution of numbers needed in your routines. And strongly consider that adding hardware random number generators beats software because you will get inexhaustible entropy pools available. Otherwise, you could drain your entropy pool, and now your routines may be predictable again, which no one wants. And finally, this is for every one of you. Hopefully, with what we learned today, we can all get lucky with Java, because that is where we want to go. Thanks everyone for participating. I've got a couple of tips here for further review if interested. First off is there actually is a full RFC written by the IETF about random numbers, and so I encourage you to, if you're interested, to review that and see what their official take on random number generation is. And then finally, on the relationship to entropy, turns out Cisco has a great introductory topic on information theory and entropy in security. So I recommend you to take a look at that. Other than that, we just hope you to visit Azul.com, learn more about both our Zulu embedded and Zulu products for IoT, as well as Zing for back-end gaming and for analytics and the back office of any IoT system. With that, I think I will turn it back to Stefan for questions. And the questions should be open. If anyone has any, they can file them in the little questions pop-up. So I got one here. Someone asked about game lag and why would we care about game lag. So I mentioned that online casinos, that there are actual online casinos powered by Java today. Why do they care about game lag? Well, lag is the delay introduced by both networks and distance between players for the packets to reach the different your screen from the backend server or from wherever the actual application running the gaming table lives. In Java, you may have pauses due to garbage collection or other sources. Using an engine like Zing as the JVM takes away a bunch of those, so it reduces game lag, improves fidelity, and it's really an example, yet another example of a low latency application, not typically what we see for Zing, which is used in payment systems and trading systems and extreme low latency requirements, but this is still a low latency environment where you want to have good response times and remove any game lag so multiple players can engage without slowing down and impeding a good flow of both card action or dice action or really any game, not just casino, but any game that's written in Java. So good question. Is game lag eliminated by Zing more significant than network performance? So that's a really good question. Obviously, network performance is a function of links in between player and server. The reality of those links are I'd say fixed by your internet connections or your network routes, but the lag differences due to JVM pauses can be in regular Java based on number of connected users or actual load on the JVM, meaning what kind of memory footprint. So there, since we have a rule of thumb on regular garbage collectors that every gigabyte of space eats potentially a second of GC time, then if you wind up with several dozens or several hundreds of gigabytes of data because you've got multiple players in your online casino, you could wind up with lag pauses that are measurable in the seconds or even minutes. So is that more obvious than lag introduced by a network hop? Absolutely. If you tell me a game is going to freeze for a minute, that's a problem. So the lag that is attributable to GC pauses can dwarf that from otherwise crisp network links. So, I mean, if you're already behind a minute lag on a network link, you need a new network. Any other questions? I got maybe one more. So, I get often asked, I mentioned earlier that I like craps. Why do I like craps? Because it's very, very close to true odds. Dice have no memory from prior rolls, which is nice. The house advantage, if you know how to play odds, can be taken down to just almost pure odds. So you've reduced the house advantage, so it's a pretty fair game. But a lot of people really like poker. Why do they like poker? Poker is very interesting because even though the randomness is introduced during the shuffle, the outcomes almost, there's an element of the outcome that's due to the cards that are held by the players, but very often the outcome is determined by the bets. Can you force an opponent into a situation, or can you, obviously poker encourages bluffing, where if you don't have the cards, you still could win based on how you position yourself in your hand. So very interesting gameplay, probably the complete opposite of complete randomness as determined by dice, more like humanistic, psychological, so very different gameplay, but still interesting. And if you're into that, the World Series of Poker just finished their November 9 tournament, which was a great example of both gameplay and human factors, but also payout. The winner took home $8.1 million, so not bad for a week's worth of playing games, really. I think that's all. I don't see any more questions in the queue. I appreciate everybody coming today. Stephen, I don't know if you have any closing remarks, but appreciate it, and thanks for listening. I think, as Stephen said, we have the recording, and I'll put my slides up to let you review shortly. Look for that email to come out in due time. Thanks a lot. Have a great day.